Hi class, welcome to the next and last section for chapter 11. So this is the last section on differential equations. Today we're going to talk about homogeneous second order linear differential equations. So the homogeneous means it's equal to zero. Linear means that the highest power of y that we see is one. Second order means that the largest derivative that's present is the second derivative. Okay. Now these are really fun to solve, actually. The only thing besides knowledge of differential equations, the only thing you really need to know in order to solve these is how to factor. Okay, these are all second order, so you don't have to get into any crazy factoring methods. You can use the synthetic division like I like to use. Um, However, they're quadratics, so you really shouldn't need it. You can use a quadratic formula if you need to. In fact, you probably will quite often. So this is a rather fun section, I think, right? So if our equation has the form a constant multiple times the second derivative plus a constant multiple times the first derivative plus a constant multiple times the function itself equaling zero. So again, second order linear homogeneous equations. So this is the general form of a second order linear homogeneous DE. So if it has this form, then we can solve these things where A, B, and C again are constant multiples. We can form an auxiliary equation that we can solve algebraically using factoring and the quadratic formula. Okay, so I would substitute my y prime with m, okay, and y double prime with m squared. Y completely drops out, okay. And now the answers to the solution are not the answers to the DE, but they help me to form the answers to the solution to the differential equation, okay. So the solutions here, again, help me to find the solution to the DE. The solutions to this quadratic are not the solutions to the DE. So we break this down into three cases, depending on what solutions we have here, okay? So the first case is that M1, M2, which are the solutions to this quadratic, are distinct real roots. So what does that mean? It means M1 is a real number, M2 is a real number, and M1 and M2 are not equal to each other. Okay, so different real values. Then the solution is going to have the form for my differential equation is the function, the solution is C1 times e to the M1 solution to the auxiliary times x plus C2e times M2 times x. Okay, so this is what my solution will look like to this second order linear homogeneous diff EQ. If the solution to the auxiliaries has distinct real roots, different real values. Okay. The second case is that M1 and M2, the solutions to these, are the same number. Okay, so I have a double root, a double solution. If M1 is equal to M2, repeated real roots, then my solution has the form y equals C1 e M1x plus C2. Very important here. I have an x times e M1x. Again, M1 and M2 are the same, so it shows up twice. In order to keep these what is called linearly independent, one of these does not have an x, the next one does. Let's say this was like a fourth power dE, and I had a fourth power auxiliary equation. Every time I would add on a new, if all of those solutions were equal in value, it would go C1, C2x, C3x squared, C4 x to the fourth, so forth and so forth and so forth, all times e times that repeated root to the x power. Okay, so that's how that would work in higher order. So again, note that we multiply by x in the second term here to keep the terms of the solution what is called linearly independent. If you don't know what linearly independent is yet, that's fine. You will hear this a lot in linear algebra, a lot in linear algebra, and a lot in the differential equations course as well, because those two courses are very, they have a lot of intersection in them. Okay. Now, my last case, again, we're looking at quadratics. The last case for this quadratic is that I have roots that are imaginary, right? Okay, case 3 is two imaginary roots. So they are complex conjugates of each other, alpha plus beta I. Then that means M2 is automatically alpha minus beta I. Then the solution to my diffie has the form the C1 constant multiple times E alpha x cosine only the beta, not the I, and not the negative part of beta, just beta. Beta x plus C2 alpha times x sine beta times x. So these two are identical, except for one is cosine and one is sine. Okay, and the C1 and C2, obviously. So let's go ahead and do an example. Okay. Um, Again, I know that we're talking about second order. I'm going to do an extreme example just so that you guys understand how this works. Okay. And for you guys, you should not have anything higher than the second order show up, but I'm going to show you a sixth order, even though the title of this is second order. Um, because if I do an extreme example, it'll make more sense to you. Okay. So here we have 2 times y to the sixth order, right? The sixth derivative, 9, negative 9 times y to the fifth derivative, fourth derivative, third derivative, second derivative, first, and just a function y. So our auxiliary equation here is going to be m to the sixth, m to the fifth, m to the fourth, m cubed, m squared, m, and then a constant term. Okay, so my auxiliary equation is this. And all the roots here, so the solution of this big old polynomial is going to tell me all the solutions to my linear, in this case, sixth order DE. Now you might be thinking, like, what, Professor Williams? Trust me, don't worry about it. Just because it's a 6 and we've been talking about 2's here, everything works exactly the same. And I'll show you exactly how that is. So using synthetic division, since this is such a large polynomial here, I look at all of my possible solutions. So I'm looking at all the factors of 2, all the factors of y. We've talked about this a little bit before. You can go to previous videos and look at the synthetic division. So the rational zeros gives me possible solutions of numerator 1 and 5 plus and minus. Okay, so P over Q. So plus or minus 5 in the numerator, plus or minus 1 in the numerator, in the denominator, plus or minus 2, and plus or minus 1. So all the factors of 2 in the bottom, all the factors of 5 on top, and all the combinations of these. So I have 5, 5 halves, 1 half, and 1. Plus or minus, all of those are my solutions. So I really only have 8 solutions. So 1, 2, 3, and 4. Okay, and then it's plus and minus, so there's actually 8. So plus or minus 5, that's that 5 over 1. I'm going to try to stick to whole numbers as much as possible, I think. So the next one would be 1 over 1. The next one would be well, 5 halves is actually larger than 1. So I think we go 1 half, 5 halves, and that's it. Okay. So there's 4 numbers here, but it's plus or minus, so there's actually 8 possible. The easiest ones to start with are the whole numbers, right? Fractions work for the synthetic division, but whole numbers are better, especially the ones I'm always going to start with plus 1. I'm going to exhaust my options, and then I'm going to go to negative 1, exhaust my options, and then the rest should be pretty straightforward from there. So the easiest zero to start with is, let's say that m equals 1. So my synthetic division, so meaning m minus 1 is the factor, so synthetic division looks like this. Again, I'm just writing my polynomial, the coefficients, 2, negative 9, 11, 8, negative 18, 1, 1. Right? 2, negative 9, 11, 8, negative 18, 1, and 5. Okay. M equals 1, so I put a 1 here. These two things multiply. Okay. And I actually, there's an imaginary 0 here. So first thing I do is I add those together and I get 2. So the 2 always drops down. I multiply those together, I get 2, and that's what goes here. I add these, I get negative 7. I multiply that times the value here, that's negative 7, so I put that here. I add, okay, get my result of 4. I multiply, and that goes to the next spot. I add, I get 12. I multiply with 1, and that goes in the next spot, so 12. I add, I get -6. I multiply that here, and it goes in the next spot. I add, I get -5. I multiply, I add, and I get 0. Again, 0 means that this is a factor. It means I did everything correct. So n minus 1 is a factor, because if I was to subtract this over, I would get n minus 1 equals 0, which is a factor of this thing. So now my new polynomial, which was a 6th degree, is now a 5th degree, because this remainder is 0. So 5th, 4th, 3rd, 2nd, 1st power, and the constant, and this completely goes away. So then now I start again, and I try using 1 again since it was successful. Okay, n minus 1 is the factor of the auxiliary. So I'm going to try this again until it fails. So the next polynomial is the result that I ended with, and I will put 1 in front again. So 1 in front, I have the coefficients, the 2 drops down, multiply, 2. Okay, add these together, I get -5, multiply, I come here, I add, I get -1, I multiply, and it comes over, I add, I get 11, I multiply, it comes over, I add, okay, I have 5, I multiply here, and I add, and I come out with 0, which means it's a factor twice, okay? So far I have it as a factor once, a factor twice, and then the remainder. So this is now a 4th degree, 3rd, 2nd, the 1st degree, m, and the constant, and this is the remainder, which is 0, which means it's a factor. So that's why I have 2 minus 5, -1, 11, and 5. And n minus 1 is a factor twice. It worked the second time, so I'm going to try it again. Okay, so I use what's left over, boom, and I start over. The 2 drops straight down. I multiply, get 2. I add to -3. I multiply, I get -3. When I add, I get -4. Multiply, it comes over. I add, I get 7. I multiply, the result comes over. I add, I get 12. I've run out of numbers. I did not end with 0. That means that this did not work. That means it was a factor twice, but not a third time. Okay, so m equals 1 has a root of multiplicity 2. It works twice. So what I'm going to do then is I'm going to try the next one, because now I want to finish factoring this, right? I've whittled it down to a 4th degree auxiliary equation, and I would like to find the solutions here. So the next one I would use would be -1, because it's the next easiest, right? So this did not work on the third result, so it is only works twice, multiplicity 2. The next easiest possible 0 is to use m equals -1. So that would mean that m plus 1 is a factor, and then we're going to do the same thing. 2 drops down, multiply, the result comes over, I add. Okay, I get -7, multiply, changes to a positive, I add, I get 6. I multiply, I get -6, I add, I get 5. I multiply, I add, I get 0. So that means -1 is a factor as well. So far I have n minus 1 twice squared, and n plus 1 once, and then this cubic. So I'm going to go one more time since it worked, and we're going to see if it works for a second time. Okay, so I go one more time, and I'll just leave this here, but you can see that when I add, and multiply, it did not work again. Okay, so next we'll try -1/2. If that doesn't work, I'll try 1/2. I could try 5 as well, since that's a nice whole number, but the -1/2 works. So how does this work with fractions? Exact same way. 2 drops down, and 2 times -1/2 is a negative. Add those, you get -8. Multiply that by -1/2, you get the 4. 6 and 4 is 10. Half and negative, and I get 0, which works out. Okay, which is very nice. Okay, so far I have n minus 1 twice, m plus 1 only once from that -1, and the 1/2 looks like this, 2m plus 1. Now, from what I have here, right, I have a quadratic. So I should be able to solve this normally. Again, 2, -8, 10. So since I have just a standard quadratic, yeah, I should be able to just, I can factor out the common 2 and then pull these apart, right? So if necessary, I'd have to use the quadratic formula for the remainder. So if I were to pull this 2 out, I would have m squared minus 4m plus 5, which we have here. Okay. I'm going to use the quadratic formula because this doesn't factor, right? In order to get a negative out, I'd have to have, or I'm sorry, a positive out, I need two negative factors. I can't have two negative factors that multiply to 5 and add to -4. There's none that are there, right? I couldn't use plus 5 or minus 5 and plus 1 because then this would be negative. So I'm going to go ahead and use the quadratic formula. Okay, m is going to equal negative b plus or minus b squared minus 4ac divided by 2a. In this case, I pulled out the 2, so a is just 1. Okay, so I'm going to have 16 minus 20 square rooted 4 and 2 here. Okay, 4 and 2 turns into 2. Square root of negative 16 minus 20 is -4, so that's a -2, or 2i, I should say. And 2i over 2 is going to be just I. So my answer here is 2 plus or minus I, the two complex conjugates. So for my A value here is 2, and my B value, or my beta, I should say, is just 1. So this polynomial can now be factored into this form, okay? M minus 1 twice, m plus 1, 2m plus 1 from this 1/2, and then my complex conjugates. M minus the first factor, right? 2 plus I, and m minus my second factor, 2 minus I. Again, think about the negative sign being distributed in that case. Okay, it doesn't really matter because they change signs. Now, these solutions that I have here, okay, 1 twice, -1, -1/2, and these complex conjugates, well, guess what? Look what happens here. Through my cases, I gave you a little bit of each one. I have some things that show up only once. Okay, I have some repeated roots, right? I have one shows up twice as a solution. Okay, and I have all three. So this is a nice way for us to kind of combine what all of these would look like together. Okay, so right, again, this is for you guys where if it's only second order, you just have to use the quadratic formula and factor as normal. Okay, so we have all of our solutions. Okay, I got the 1/2, -1/2 from this. I got my -1 from this one. I got my repeated root of 1 from this, and then my complex conjugates here. Okay, so throwing that into my form, I'm pretty sure I'm going in order. The -1/2 only shows up once, so it'll be C1 e to the -1/2 x. Okay, this -1 only shows up once, so I have plus C2 e to the negative, or I'm sorry, plus C2 e to the -x. This shows up twice, so I'll have plus C3 e to the x, and then the next one will not be C4 e to the x because that would just add them together, so it'll be C4 x e to the x. Okay, so this root is a repeated root, so I have that x that shows up, and then I'm going to take my um, complex conjugates, right? I just need the alpha and the beta. So the first one is going to be C5 e to the alpha, so 2x, times cosine x, because this beta is just 1. And then the last one is going to be C6 e to the 2x, because that's the alpha, sine of x, because the beta is 1. I'm not using the negative. I'm only using the value of beta. There's just the 1 there. And so that is my full solution. It has a single value, a repeated root, and the complex case. It has a little bit of all of them. And so anything that you do in this class will have way less solutions. It'll be way easier to solve. You won't have to use synthetic division. You'll only have to factor or use the quadratic form. And so that makes this really, really easier. But you can now apply these methods in these cases to higher order linear homogeneous equations as well, if they were to pop up. Okay, and that's how that works. All right, I'll see you guys in the next chapter where we discuss polar coordinates and coordinates.